Welcome, ladies and gentlemen, to our continuing study of rotational motion. I suggested to you in the last lesson that you can think of this unit and the next unit as going through again everything that we've done so far this year, but at a rotational level. We are basically developing a rotational equivalent for all the linear quantities that we're familiar with. Today we're going to focus on force and mass. Let's get started. If you look on the screen, you see an object that has three different forces being applied to it. Now, the magnitude of the forces is the same in each case, okay? Call it 10 newtons. But notice that the point of application of the force matters, okay? If you apply a force at F1, okay, basically you're just pulling the circular object to the left, right? That force is applied on a line that runs through the center of mass of the object. When you apply a force that runs along a line that also runs through the center of mass of the object, that object will move in a line only. It will only translate. But if you apply a force like F2 or F3, you're going to make the object translate and rotate. Okay? And that's what we want to look at today, because when a force is applied off-center, so to speak, right, when it's applied along a line that does not run through the center of mass of the object, then you're going to get rotation. So, what I want you to consider is we're gonna break this object up, okay, this disk up into a series of objects, and we're just gonna say, hey, let's look at this object. Let's call this MI. Okay, that's the I particle, so to speak. Okay, and we're just gonna look at the force on that particle. Okay, well, it's F equals MA, right? MI. Okay. And except we're going to substitute some of our new quantities in. Okay, so instead of A here, we're going to write MI. We're going to write R alpha. Right, and that's the angular acceleration of that particle at that point. Okay, and then we're just going to consider that force F3. Okay, that's going to be our force. Now, just for kicks here, I'm going to multiply both sides by R. Okay, and I'm going to get the following. This is going to get squared, like so. All right. The quantity on the left is going to get a new name. This right here is called the torque, and we use the Greek T, the Greek letter tau, okay, for torque. And on the right side, you'll notice something very interesting. If we group this quantity together here, right, like that, if we group that together, okay, notice that this formula still kind of follows the form of F equals MA if we treat this new quantity here as the mass. And that's exactly what we're going to do. In fact, we're going to assign it a new letter. We're going to call it the letter I, and that is the moment of inertia. Okay? And what we get here is Newton's second law in rotational form. Torque equals I alpha. Okay? Where we have the rotational equivalent of force, torque, applied to the rotational equivalent of mass, moment of inertia. All right, and that means that the moment of inertia is defined as how far that mass is from the axis of rotation. In other words, what this tells us, okay, in more practical terms, is that for a given amount of mass, it matters how that mass is distributed in terms of how it's going to rotate. Okay, so the same amount of mass distributed differently, right? 10 kilograms distributed one way will rotate one way, but that same 10 kilograms distributed another way will rotate another way. The most well-known poetic example of this is the pirouette of the ice skater on the ice, right? She can pull her arms in, redistribute her mass, and rotate differently than if her arms are out. It's the same mass distributed differently. Back to Newton's second law in rotational form. We're going to use Newton's second law in rotational form in more detail in future lessons. We're going to apply it to problem solving. Today, however, we're going to just focus on the moment of inertia and how to find the moment of inertia for different systems of objects and different shapes of objects. We're going to take a look at this example here. You have four objects that are connected. Okay, they're rotating as a system, as what we call a rigid body. Okay, so they're connected by these massless rods. They're in a rectangle. Okay, it looks pretty close to a square here, but we have two different quantities. Okay, a rectangle of one side length 2b, right, some constant, and a width of 2a. And this rigid object is rotating around an axis that runs through the center. Okay, so in this particular configuration, we can calculate the moment of inertia by applying this to each of the objects. Okay, so when you have a collection of objects, you're going to have to sum up over all the different ones. You're going to take each individual moment of inertia and add them all together. Hopefully you'll see that each mass, right, is a distance a away, right? Not the actual point-to-point distance. In other words, notice we're not measuring like from the center of the object out like that. That's not the distance that we're measuring. We're simply measuring the perpendicular distance between the axis and the object. Okay, and that's just going to be a. And we just have this 4 times, right? Because we've got 4 objects that are basically the same distance apart. Right, so we have this right here. Just have this 4 times. And the total is pretty easy here. It's just 4ma squared. Okay, that's the total moment of inertia of this system when it's rotating through this particular axis. Right, now if you take this axis and you move it, let's say that let's not rotate around this axis, but rather let's rotate around, say, an axis going through here. Okay. Well, now this value, you could work it out for yourself, but this value is going to change. Okay, it's not going to be the same for a given object. It depends on which axis you're rotating on. Okay, so this is an example of working with a system of particles, finding the moment of inertia, right, where you do each particle separately and then sum them up. But you know that we also sometimes are presented not with a system of particles, but continuous objects. So here on the next screen, let's consider some specific types of continuous objects, okay? For example, a sphere, right? Some of these common shapes that we come across. Or another common one is that of a cylinder, okay? A cylinder. And again, the axis around which you rotate matters as to what kind of moment of inertia you're going to have, right? If I take the sphere and I rotate through there, that's different than if I take this sphere and rotate around that axis, okay? And same goes for the cylinder, okay? For the cylinder, right, there's different axes through which I can rotate this mass, right? I can rotate around that axis. I can rotate around that axis, right? I can rotate around that axis. What we have actually is, in your book, there's a table for the moments of inertia of different shapes of objects for specific axes. Now, the default moment of inertia is for the shape of the object to be rotating around an axis that runs through its center of mass, right? For example, this right here. So this is given in your book as 2/5 mr squared, right? Mass times the radius of the object, 2/5, like so. Okay. And for the cylinder, we have the moment of inertia through this axis here as being 1/2 mr squared. Okay, so different shapes are going to have different terms. As you work with these, you're going to get familiar with them. You're going to memorize a lot of them. How do we arrive at these terms, however, right? How do we get that for a continuous shape? Well, as you've seen in previous units, okay, we take the sum of, right, for a discrete set of objects, like so. And if we have a continuous shape, right, this is going to become the following. It's going to become an integral. Okay. So let's take a look at a specific example. Let's take a
uniform rod. Okay. And let's say that this rod's being swung about an axis that's at one of the ends, right? So it's not being swung around the axis that runs through the center of mass, right? That would be this one here, right? It's not going through that axis. It's going through one at the end. So it's like you're taking a ruler, holding it at the end, and sort of spinning it around on its end. Okay. If we want to find the moment of inertia of this object, we're going to be using our newfound calculus version of moment of inertia, right? So what we need to do is we need to break down that mass element, right, which I've marked there a little bit from the center, okay? And we're going to use the linear density trick that we learned last unit, okay, which is that we can define the linear density of an object as the mass of the object divided by its length, okay? So that mass element there, right,
its mass can be expressed as the linear density times its length, which is dx, right? So if we measure distances from the axis of rotation, okay, this would be x right here, right? This is the distance. So we're taking that mass element. That's a distance x from the axis, okay? And that has a width dx, right? And we're taking that mass element and we're integrating over all of those mass elements, right? From here, right, all the way out. We're taking all those mass elements all the way out to the distance L, okay? And that's going to look like this. So we're going to integrate from 0 to L, x squared. And now for dm, we're going to substitute in the m over L dx, right? Which is a constant, okay? So we have the following, we pull this out front. We're looking at this right here, like so. And when you do that, okay, you're going to get m over L, x cubed over 3. You're going to get ml squared over 3, right? Because the L on the bottom is going to cancel one of the L's on the top. So there you have it, moment of inertia of a continuous object, right? The AP College Board does expect you to be able to do an integration like this. And again, they're only going to expect you to be able to do it in one dimension. Okay, so for a rod. We want to look at one more aspect of moment of inertia, and that's known as the parallel axis theorem. I'm going to show it to you actually in the context of the previous example that we've already determined. Okay, so in this previous example, we had these 4 masses, right? These 4 identical masses that were attached by massless rods. Okay, where this was a length 2b and this was a length 2a. Now we had already determined that for the axis that runs through the center, okay, if this system of objects rotates around that axis, we determined that the moment of inertia, right? You might call that ICM, right? Because it's the axis that runs through the center of mass of the system. That was 4ma squared. Okay. Well, what if we instead wanted to do, like I mentioned earlier, what if we wanted to not rotate around that axis at all, but rather rotate through another axis that runs through here? Okay. What if we wanted to know the moment of inertia of the system for that? Well, that's where this cool thing called the parallel axis theorem comes in. It relates the moment of inertia around the center of mass axis to the moment of inertia around the axis that you want to investigate. Let me write it down. The moment of inertia around our new axis is going to be the moment of inertia around the center of mass axis plus this quantity here, okay, where h represents the distance between the center of mass axis, okay, and the axis that you're investigating. So in our case, right, the distance between these two is a. So the new moment of inertia of this system is going to be 4ma squared, right, which is our original result, plus 4m, right, the mass of the system, times another a squared. So it's actually going to be 8ma squared. Okay? And that shows you that the same mass rotated around a different axis will rotate differently. It actually, in effect, acts heavier, okay, because you have a mass that's twice as far away, right? Now, you only have 2 masses instead of 4, but those 2 masses are twice as far away, and notice that the factor, right, the factor of distance gets squared. All right, there's your first look at moment of inertia.